we're going to need a few of these formulas, so I'm just going to write them on the board now. So when we come to it, we'll have them available. Let's see, first one for these chapters, I think we're going to need ones that I can't readily remember. Some of them I can, so we won't put those up there. How about this one? Well, let's put Gibbs free energy up here. Got that one. And then this one, relationships to K. Minus RT log K. Okay, for sure we'll need that one. Oh, and this one, I don't even think this one has a name. Lots of times they have a name associated with them. Based on who proposed this setup first. It's 0, 0 over R, is it? Okay, let's see, what else? Oh, this one, delta S surroundings over T. And as a corollary to that one, if equilibrium and delta S system equals the positive of that one. The reason for that is delta S total equals delta S system plus delta S surroundings. If we're at equilibrium, then delta S is 0. So these have to be opposite signs of each other. And let's see, did I miss one? For this chapter, I think we're good. Yeah, I think we're okay. All right, so let's go back to the top. Is there any ones that we need to get to for sure?
It's volume 2, it's like 20 to 22.
Okay, let's go back down and look at that one. See if I've got them marked. 20, 21, and 22. Okay, I'll tell you what. It looks like those are each based upon the same. Well, there's 20. 21 and 22 are based upon the same reaction. They're just asking different questions. Okay, so how about, let's see, can I do this? Get this out of the way. And I want to highlight here. Make sure that one's marked. Come on. How come it didn't mark? Highlight. Huh. Well, just remind me when we get there. Probably because I'm sharing and it's not going to let me edit it. Okay. I think we take them in order as the ones I've got marked. Then by the time we get to 21 and 22, it may be clearer. Okay. So let's set this one aside. It's not binding. Version 1, number 9. At 1 atmosphere, liquid water is heated above 100 degrees. So that means we're above the boiling point. We're no longer at equilibrium. So delta S surroundings for this process would be what? Well, if we were at equilibrium, then we'd have these two equal to each other but opposite signs. If we're past equilibrium, then the delta S total is increasing because we're adding more energy to the boiled water. So if delta S total is greater than 0 and delta S surroundings is a given value, then what we're doing is, let's draw a picture. We have the system here. We have the surroundings here. And the delta S surroundings, no, that's not the proper application. What we're doing is we're adding energy from the surroundings to the system. And if we're not at equilibrium, then system is gaining more energy entropy than the surroundings is losing. So that means this one is bigger than that one, and this one is going to be negative. This one's going to be positive. So this one, the surroundings is going to be greater than 0, less than 0. Oh, surroundings, excuse me. 9 is surroundings. So this one is losing more, and this one is gaining more in order to give us a positive delta S. So, okay. So I already answered 10. 10 because delta S above equilibrium situation is got to be positive. So that means this one has to be positive and this one has to be less than 0. If that makes any sense. As much sense as possible under these circumstances. Okay, let's look at number 11 now. We knocked out 9 and 10 in one shot. Which of the following is true? Okay, each one of them starts with by spontaneous. So what do we mean by spontaneous? Spontaneous simply means that the reaction proceeds without any intervention. All right. As written, if we're saying spontaneous, as written from reactants to products, we're saying that it always proceeds to the right if it's spontaneous. If we do this, then that direction is non-spontaneous. So to the right would be spontaneous. So which ones satisfy that condition? A satisfies that condition, the first condition. B is wrong. C proceeds, no. C goes to the left, B goes to the left, that's wrong. So it's either A or D, looks like. Now we have to separate, tie break. Always proceeds to the right as written, even if very slowly. Even if very slowly. So both of them are in agreement so far. So what's the next statement? Increasing the temperature may speed up the reaction, but it does not affect the spontaneity. That's false. Spontaneity can be increased by increasing the temperature, and we just saw that. With increasing the temperature above the boiling point, we have made this value positive, which means spontaneous. We're not at equilibrium there. So B is false. Let's see. I should have put B there. B is false for that one part of the statement. D actually says increasing the temperature may speed up the reaction, and it generally affects the spontaneity of the reaction. We say increasing the temperature may speed up the reaction. When would it slow down the reaction? Well, it would shift the equilibrium. Actually, increasing the temperature no, there may be other factors. Okay, I can't say. That's true. May speed up the reaction. It gives you more activation energy. But if you're fighting another condition like number of moles of gas on one side or the other, then you may have a resisting force. So may speed up the reaction is correct, but it generally does affect the spontaneity. Yeah. So that gives D the best shot at being a true statement. Let's see. Who's next? Oh, we skipped quite a few. Get down into the 30s. I think a lot of those that I skipped, we're going to cover in version 2. So let's see what 34 has to say. The following reaction, carbon dioxide plus water yields methane plus oxygen. And the delta H is 803 kilojoules, which means what? It's endothermic. Which of the following will increase K? This is fairly simple. In fact, we go back to the previous chapter, actually. Reactants, products. If it's endothermic, that means our delta H is on this side. Right? So if the K, before we do that, before we change the temperature, if the K is equal to, let's just be generic, products over reactants. Okay. Now, if we, which of the following we increase K? If we want to increase K, we want more products and fewer reactants, right? Okay. How are we going to get more products and fewer reactants? Increase the temperature. That'll drive the equilibrium to the right, and that'll change the amount of products versus the amount of reactants. Okay. So, we have several options here. Okay, these are all gases. So if we decrease the number of moles of methane, now decreasing the number of moles doesn't change the K at all. Right? It changes the equilibrium position, but not the K, by just changing the number of starting materials. Increase the volume. Well, that won't affect the equilibrium at all, because we have equal moles of gas on either side, 3 moles of reactants and 3 moles of product. But even then, it wouldn't affect the K. The K is still constant. The only thing that can affect the K is temperature. Increase the temperature of the system. Yes, we input K here. We shift to more products and fewer reactants, which increases the K. Let's see, 36. This gas phase reaction, and we've got delta H and we've got a K. What would be the effect on the amount of NO present of compressing the equilibrium system to a smaller volume, multi-temperature constant? This has a lot of information up there you don't need. Because if we've got NO plus a half O2, that's an unconventional setup there because we're using a fractional coefficient. Two. And the delta H is negative. Well, Temperature is constant, so we don't have to bother ourselves with the delta H. We hold the temperature constant. K is heavily favored to this side. K is much, much greater than 1. So what will be the effect on the amount of NO of compressing the equilibrium system to a smaller volume? If we compress the system, we're increasing the pressure, and we've got 1.5 moles here, and we've only got 1 mole there. So if we compress the system, it's going to try to shift to the right to relieve some of that pressure, because there are more moles over here than there are over there. So we're going to decrease the amount of NO in our in an equilibrium situation. So the amount of NO will decrease. Okay. So far, it feels like we're back in chapter. What chapter? 16. That's okay. It's all an integrated problem. 46. Given the following data, calculate the normal boiling point for formic acid. Okay, formic acid. For the boiling point, we're going from this liquid to that gas. We're writing it this way because if we have that, and this, and that, that's formic acid. So this COOH is this group right here, that carboxylic acid group. I need another marker with a little more get up and go. All right, so we want to know the normal boiling point, and we're given, and we need this equation because we're going to have to calculate the delta H and the delta S. And the reason for that is this situation right here. We need to know the delta H and the delta S for the system. If we're talking about equilibrium and we're talking about the system situation, we want the one with positive multiplier, not the negative. Negative talks about surroundings. We're talking about the system here. So we're looking for input to satisfy this equation, which means that would be the boiling point because we're at equilibrium. So that means we need this and delta H over delta S. Okay, so how do we calculate each one? Well, we need delta H, and delta H for this reaction is going to be the product minus the reactant. So the product is a gas. It's minus 363. Right? And then subtract the delta H for the reactant, which is minus 410. Which I would normally do this in my head, but I don't trust myself today. It is 47. This is 47 kilojoules. Remember, the delta S is in terms of joules. And very often the delta H is in kilojoules. So we have to match apples and apples. That means this is 47 times 10 to the third joules. Okay. Delta S then is equal to a similar arrangement. Product 251.1 minus 1/3. And that's in joules already. This is 121.1. Okay, joules. So now we just plug in the numbers. This is 4.7 times 10 to the fourth. And this is, well, actually, that's joules per T. This is joules. And this is 121.1 joules per T. That way the joules cancel, the T flips to the top, and we have the right temperature. Well, we do in Kelvin. All right, so we got another step. So let's take this one and let's see. Divide and times. So this is that right? Let me do that again. Exponent 4. 121.1 divide. It's better. This is 388. Close enough. Minus 273, right? Would give us, this is K, we want degree C. So that'd be 115 degrees C. Okay. All right. Scroll. And we come to 52. Time. We want to know the delta G for water plus half oxygen yields hydrogen peroxide. Water, gaseous state, plus 1/2 O2 gas, and that yields hydrogen peroxide gas. And we're given a temperature of 600.1, 600.1 K. We may need that, we may not. Use the following data, and we want to calculate delta G. All right, delta G 0 is going to be, this would probably work best, right? Since we're given K values, then we'll use this one, but we have to find the K for that reaction. And we're not given the K for that reaction. We're given the K for components. So we're going to have to use Hess's law to find out what the K is for that reaction. Right. Let's see. Hydrogen peroxide, the first equation, hydrogen peroxide is on the right, as it should be. So we can incorporate that one. This first reaction is hydrogen plus oxygen yields hydrogen peroxide. And the K here is equal to 2.3 times 10 to the 6th. Okay. So we got this part. And now we need to get water on this side. Water's on the wrong side there. Right, so we need to flip the equation and divide by 2, right? Because there's 2 waters there, we only need 1. So we need water on this side, and then 2 hydrogens on this side. I'm going to divide by 2 in just a second. Plus O2 gas. And this K2 then is equal to the inverse, right? Because we flipped it. 1.8 times 10 to the 37 would be, let's do that, because we flipped the equation. But now we're going to divide by 1/2, correct? Because we only need 1. So what does that do to this one? It's raised to the 1/2 power, correct? So we take square root of it. Okay, so let's see if that gets us what we want. That gives us 1 there, 1 there, and a 1/2 there. So a 1/2 on this side and a whole on that side yields a 1/2. We're good there. We got an H2 on this side and an an H2 on that side. They go out. Got one of these, one of those. We converted this one into a 1/2 there and this one, so we're good. So now we need to find out what the K is by multiplying those two, right? All right, let's do this one first. I'm going to take the inverse 1.8 exponent 37, right? Yeah. And then I'm going to take the inverse of that, right? 5.56 times 10 to the minus 38, and then take square root of it. Right. So this is equal to 2.36 times 10 to the minus 19 times 2.3, 10 to the 6th. So if I did this right, that's our K. And where did I say it was? Here. Delta G0, which is what we're after, correct? That's equal to R, which is 8.3145 joules per mole K. And then temperature is 600.1. We got a negative here. Negative right there. And then log K. Now see if that gets us anywhere near our expected value. I'm going to go ahead and change the sign. I think that's right. No, let's go ahead and take the log of that natural log. There we go. Now I'm going to multiply it by that negative, which means change the sign, then by 8.3145, and then by 600.1. And I get delta G0 is 1.41 times 10 to the 5th joules. Oh, they want kilojoules. Right. Yep. So if we take the kilo out of this one, that reduces that one to 10 squared, right? And this one would be 1.41 then times 2 is 141 kilojoules. Let's see. Before I erase that, I don't think I need it again. I got one or two in here where they're separated, but they're based on the same reaction. So I try to keep those together. I think I flagged them already, so I should erase stuff that we need afterwards. 53. Consider this reaction. 2NO2 equals N2O4. It's got the delta H0, the delta S0 in a container at 298 K. So what's 298 K? Standard temperature. That's 25 degrees C. And their initial pressures. Okay, so let's write this equation. 2NO2 gas is in equilibrium with N2O4 gas. Okay, delta H 0 is minus 56.8. And delta S0 is minus 175. 5 joules per K. And the initial partial pressures before the reaction begins are 2.4 atmospheres for N2O4 and 0.42 atmospheres for NO2. Okay, that's everything that's given. So which of the following statements is true? N2O4 decomposes into NO2, that is, it goes back this way. Or NO2 will dimerize to form that. System is at equilibrium. Final total pressure must be known to answer this question. Well, we don't need the final pressure. What we need is a comparison of those conditions to the K. So we need to be able to calculate Q versus K to tell which way it's going to go, because we've got amounts on both sides, right? If we have one of them were zero, it'd be easy. But we've got amounts on both sides, so we need to know what K is. All right, we've got delta S, delta, and delta H, and we want to know K. All right, I think we need to combine these two. And these would, of course, be under standard conditions. If we combine these two equations, then we'll keep K in the expression. We can calculate K because then we'll have included delta H and delta S. Okay, so if we have delta G0 equals delta H, 0 minus T, delta S, 0, and we're going to combine that with delta G0, well, that's equal, equals minus RT natural log K, then we're saying that this expression is equal to that expression. Let's see, let's just write that out. Delta H0 minus T delta S0 equals minus RT log K. All right, let's see. Can we simplify this any further? Might as well just leave it there. We've got delta H and delta S. This one needs to be in joules. So this would be minus 56.8 times 10 to the third joules. So delta H is going to be minus 56.8 times 10 to the third joules. And then minus T25 or 298 K times minus 175. And this is minus 8.3145 for R. And then 298. Yeah. 298. And then log K. I think the way I worked out the problem, I went ahead and solved this one for log K. But this ought to work. Okay. Let's do that one. 298 times 175, negative 175, and then negative times that, or subtract it from, let's see, negative, and then 56.8, negative exponent 3, add them together. So if I did that right, I got minus 4.65 times 10 to the third. And this is minus 8.3145 times 298. And that's minus 2.48 times 10 to the third equals times log K. So log K then is going to be equal to this one divided by that one. Is that right? Change the signs. This one into that one. Okay. And this is 1.88. So what's K? Well, it's e to that power, isn't it? So I get 6.3, so 0.53. 6.53. All right. So that's K. Let's calculate Q. Q equals 2.4 atmospheres divided by 0.42 squared. Here we go. And divide. So that's 1.36. That's Q. So K is greater than Q. We got too much on this side, not enough on that side, because K is greater than Q. Or Q is less than K. Q is less than K means we don't have enough on this side. So we're going to decompose N2O4 into NO2. That's A. Well, that's a lot of work just to get one simple answer. How about 56? Okay, well, consider the following system at 25 degrees standard. PCl3, we did one like this in class, I think, plus chlorine gas is in equilibrium with PCl5 gas. Okay. Delta H is negative 92.5 kilojoules. Okay, if the temperature, oh, this is an easy one. That's negative, right? It's exothermic. So our delta H goes on this side. If the temperature of the system is raised, then we're going to shift this way. And if we're trying to answer the question, ratio of PCl5 to PCl3 partial pressure. PCl5 to PCl3. We raise the temperature, it's moving this way, so that one's going down, this one's going up. And the ratio is going to go down. Right? So we'll get a decrease in the ratio of PCl5 to PCl3. I thought it was going to be hard. That one was easy. Okay. Okay, here's one. We're going to do 58 in this one, then we're going to go down to version 2, 56, and use the same circumstances to answer a different question. So this is, up to this point, we've been in version 1. Should have marked that at the beginning. 58, sorry. Okay. The equilibrium constant for dissociation of chlorine to Cl2, and this has to be gas, to 2Cl, like that, was measured as a function of temperature. Measured as a function of temperature. Equilibrium constant measured as a function of temperature. This is our equation right here. A graph of natural log K versus 1 over T for this reaction gives a straight line with a slope of minus. So we've got 1 over T here, log K here, got a negative slope, and that value is equal to minus 1.651 times 10 to the 4th. And an intercept of 1451. So this is 14.51. Okay, for these data, which of the following statements is true? The reaction is exothermic, endothermic, rate is high, reaction is not spontaneous. All right. Let's tackle the easiest one first. Let's tackle the slope. The slope is negative 1.651 times 10 to the 4th. The slope here is delta H over R, negative delta H over R is equal to that value, minus 1.651 times 10 to the 4th. Okay. I think it's fairly obvious from this one that this is negative, that's negative. If we solve for this and just take R over here, multiply that times R, then these are going to cancel out and delta H has to be positive, right? Oh, wait a minute. Yeah. Delta H is positive because a positive times a negative is a negative. So delta H is positive. That means it's going to be on this side. And that says that the reaction is exothermic. Endothermic? Hold on a second. Review my logic here. Oh. Well, about 6 of one, half a dozen the other. Delta H0 over R equals 1.651 times 10 to the 4th. If we just get rid of the negatives there. Oh, I put it on the wrong side. That's the problem. Right? If that's positive and this is positive, we can do a negative here, it doesn't matter. This has to be a positive, which means it's endothermic. I interpreted the values wrong. Well, we found an answer. E says none of these, and we found one that was correct, so we don't have to do the rest of them. Let's see what version 256 says. Version 256. Let's go down there. And we'll come back to 59 after this. Version 256. Getting warm. There we go. Okay. Okay, looks same conditions. Intercept 40. Okay, the value of delta H for this dissociation reaction is, okay, now we want to calculate the delta H for this. Right. So we'll just take, we all we have to do is substitute R. If we put R on this side, negative delta H0 equals negative 1.651 times 10 to the 4th times 8.3145. One exponent 4 and 8.3145 times. So delta H, and I got rid of the negatives already, is 1.37 times 10 to the 5th joules. We're probably in kilojoules, aren't we? Yeah, we're in kilojoules. All right, so kilo and then 10 squared here would be 137 kilojoules. Positive 137. So that's B. Now we go back and finish chapter 1. I mean, version 1. Version 1. There. I think it was 59 coming up, wasn't it? Let's see. Scroll. We'll get there eventually. There we go. Okay, for a certain process at 300K, delta G equals, if the process is carried out, versus the amount of useful work. Oh. The question is the amount of useful work that can be performed. So we're looking for W max. I didn't put that one over here, did I? W max equals, and these are under, this is at 300K. Equals, that's the whole point. The maximum amount of work is equal to the free energy. Now, we know that we're not going to ever get that much, but this is the maximum. For a certain process, then delta G is minus 10.4 kilojoules. Minus 10.4 kilojoules. And since it's exothermic, well, exergonic, the signs are similar to our expression of enthalpy. So negative means we're going to get something out of it. So the amount of useful work that can be performed, not that may be performed, is minus 10.4 kilojoules. Oh, now we're back in version 2. All right, number 2. A 2-bulb flask contains 5 particles. What's the probability of finding all 5 particles on the left side? So we have we want to know the probability of finding all 5 of those particles on this side. Okay, let's take it one at a time. You know, probability, if you say, what's the probability for one event? What's the probability if we superimpose a second event on that? That means multiply the 2 together, the 2 probabilities. Okay. All right. So what's the probability of finding A on one side or the other? It's 1/2. Right. It could either be on this side or that side. What's the probability of finding B on one side or the other? 1/2. Or C, 1/2. Or D, or E. Right. So the probability for finding all of them on one side is 1/2 to the 5th power. So it's 2, 4, 6, 2. Let's say 2, 4, 8, 16, 32. So it's 1/32. And we need to know the answer is in percent. So let's say 32 and invert it and times 100. And that's 31.3%. Oh, excuse me. No, I multiplied it by a factor that wasn't there. 3.13%. There we go. That's the probability of finding all of them on one side. Let's see, who's next? Skip a few and 14. for this process, CHCl3, CH3, trichloromethane solid to liquid. And we're given delta H0 and delta S. What's the melting point of chloroform? Okay. Did we do one like this before? If we have delta S and delta H. Okay. The melting point then we want is here. Delta S system, delta H gives us T. T, so the melting point is going to be delta H over delta S. Okay. Delta H is 9.19 kilojoules, or 9.19 times 10 to the third joules, and 43.9 joules per mole K. There's only one mole, so it's 43.9 joules per K. That should give us the melting point. Well, this is in K. 209 K. And of course it's in degrees C. Minus 273 will give us degrees C. 64 minus 64 degrees C. Okay. We did one like that already. All right. How about, okay, we're getting into your region here. Let's do 20. In which case must a reaction be spontaneous at all temperatures? All right. So, delta G, delta H, delta S. And then we've got a T stuck in there. So in order for the reaction to be spontaneous, delta G must be negative, right? So how do we get negative under all circumstances? If it's like this, minus T delta S, then this would have to be negative, and this would have to be, hold on a second. This would have to be positive, wouldn't it? Which case must the reaction be spontaneous at all temperatures? Yeah. Delta H negative, delta S positive. That's right. That's right. I was thinking of a different one. That's it. So that's D. That would give you a spontaneous reaction no matter what the temperature is. Okay, now let's look at 21 and 22. They're based on the same reaction? Yeah. 21. Okay, so we're looking at 2Fe solid and 3 halves O2 gas plus 3 water. Am I going to have enough room here? Yeah. yields 2 FeOH. 2. Stop. Okay. Delta H is minus 789 kilojoules.
I think that's a 3 on OH2 at the end.
Thank
I'm pretty sure it's a 3 in this one.
Yep. Yeah, there it is right there in black and white. And that's we got 2 FEs. Yeah. Okay, minus 789 kilojoules per mole. All right. Determine the delta S for the surroundings for the reaction. So delta S for the surroundings is minus delta H over T. And temperature is 25 degrees. E equals 25 degrees C, which is 298 K. So that's a simple calculation. We just say delta S for the surroundings is a negative delta H, and this has to be in joules. So minus 789 times 10 to the third joules divided by temperature, which is 298. Okay. 789 exponent 3 and 298 divide. And that didn't work out. Let's try it again. 789. There we go. And these negatives make a positive. So this is going to be 2.64 times 10 to the third joule per K. Oh, kilojoules. Okay, so this would be 264. Right. That says 2.65. Oh, no. I'm sorry. This becomes kilo. Right? 2.64 kilojoules per K. There we go. That's E. And 22, what does 22 want from us? Delta G for the reaction. Okay. Delta G. We know, let's see. The only one we've got with delta G, we've got these two with delta G. We don't know K though. So I think we'll have to go to the Gibbs equation. There's another possibility. We could have calculated delta S using the enthalpies, the entropies of formation. But let's see if we can get away with doing it this way. Minus T delta S. There's more than one way to solve this problem, I think. So this one is delta S surroundings. This is delta S system, right? So that should be a negative. If this is positive for the surroundings, then this is negative. So we've got a T, 298, and then a negative 2.64 kilojoules. Let's use joules. 2.64 times 10 to the third joule per K. That'll give us joules here. This one needs to be minus 789 times 10 to the third. Minus 789. Wait a minute. Is our answer in... Oh, I'm making this harder than it needs to be. Is delta G equal to delta H? Delta G is 0, greater than 0, less than 0. Okay. I'm going, we can probably do this one without actually calculating things, right? If this is a negative, and that makes this one positive, right? And this is a negative. Oh, maybe we do need this. We do need this. This is in joules. Let's make it kilojoules. To answer the question, kilojoules work just fine. 2.64. Okay, kilojoules. And this is 789 kilojoules. Yep, kilojoules. Okay. So this is a positive, this is a negative, and this is hugely more negative than that one is, isn't it? 298 and 2.64 times. That's, well, actually, there's not a big difference. 787 kilojoules versus 789. This one's just barely spontaneous, isn't it? Yeah. So we did have to do some calculations after all. And that means delta G is less than 0, but not by much. Does that answer your questions?
Yes.
Okay. It took me a while to get my bearings. Helps to read the question beforehand. Okay, let's see. Find another highlighted one. Here we go. This one looks like one we've done before. When a stable diatomic molecule spontaneously forms from its atoms, what are the signs of delta H, delta S, delta G? Okay. A diatomic molecule forms from its atoms. So we have two X's, and these, of course, have to be gas. Spontaneously forms, it's diatomic. Okay. And if it's, let's see, we have delta H, delta S, and delta G. We want the signs for each one of those. Okay. If it forms spontaneously, that has to be negative. Right? Okay. And if we go to Gibbs, delta G equals delta H minus T delta S. We already know that this one's negative. And if we go from individual atoms to the diatomic molecule, it's going to be exothermic, right? Because if we look at it in reverse, the the bond energy, we would have to add energy into that to make it split. So that means that energy that we added in to go this way is given off when we go this way, right? So that's negative. Delta S, since we're going from 2 to 1, this is negative also, right? Less, we're going to more ordered situation, only 1 here versus 2 there. Okay, so they're all negative. $31. Get over time. Calculate solubility product for the salt sodium chloride at 25 degrees. Okay, solubility product. Sodium chloride solid gives us sodium ions and chloride ions. And then the solubility product is simply equal to, we may not need this, but I'm going to put it up there anyway. That's a K value. So where do we have K? We have K right here. Now, one thing about the delta G's. But these are not standard conditions. Right? Sodium would be a solid metal, and its delta G and delta H would be 0. So these all have values. So if we want to calculate the delta G for these, what we need is the delta G for sodium and chlorine added together, products, minus 262, and then minus 131. And then subtract the delta G for sodium chloride, which is minus 383. Right? And these are all in kilojoules. Okay. So as a first step, let's find out what the delta G is in kilojoules. 262, change the sign, and 131 minus, and then plus 838. So that's minus 9.2 kilojoules. And if we're going to do a calculation of this one right here, the units here determine what that must be. It has to be in joules. So this is minus 9.2 times 10 to the third joules. Then we can use this equation. This is delta G. Actually, that's under standard conditions. So let's solve for K, or log K anyway. That means we've got delta G 0 divided by a negative RT. So delta G 0 is minus 9.2 times 10 to the third joules, and then minus 8.3145. And temperature, standard conditions, 298 K. Okay, so that's going to come out with a positive value for the log K, and then we can solve for K. 9.2. Sure. And then 8.3145. 298 times. This one is minus 2.48 times 10 to the third. And then divide those. And I get 3.713. And K then would be e to that power. So I get 40 point, let's see, round it off, it's 41.0 actually. 0.0 is our K for that reaction. That's A. The solubility product. So that's a very large K value, which means sodium chloride is very soluble. $34. Okay, gas phase reaction. NO plus a half O2 yields NO2. Delta H is given, K is given. For this system at equilibrium, how will raising the temperature affect the amount of NO present? Oh, this is simple. What type of reaction is this? Exothermic or endothermic? Delta H is a negative, right? So it's exothermic. If we raise the temperature, it's going to drive the reaction back toward reactants. And the NO should increase. Okay. And let's see. How about 40? Oh, this is just stating the law. Second law of thermodynamics. Put it in English. Well, let's see. What does the second law state? Second law states that the delta S for the entire universe is always increasing. In any spontaneous reaction, that's true. For spontaneous reaction, delta S total is greater than 0. So let's see which one satisfies that. B, entropy of the universe increases during a spontaneous process. And that's if you consider universe as total, because this happens no matter what you do for the entire universe. But for any given process, this is true. All right. 42. Mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light from a burning magnesium strip. Okay, so this is the reaction we're looking at. It's a chlorine gas, yeah. And that's 2HCl gas. Okay. And then we have delta G, delta H, and delta S for this reaction. The delta G is negative, so this is spontaneous reaction in terms of equilibrium. Delta H is negative, which means it's exothermic. And delta S is negative, which means it's not spontaneous. Well, we can't say that. This is delta S for the system. All right, which of the following is consistent with information? Well, look at the answers. The answers are in terms of thermodynamic equilibrium or stability versus kinetics. So if we have to input energy in the terms of these things are contained in a glass enclosure, and then we have this magnesium strip out here that's reacting with oxygen to send energy into there to make the reaction. So the strip's not in here. The strip is sending its energy versus by way of light. And that's enough to get the reaction going and release energy. Okay, so what can we say about that? The reactants are thermodynamically more stable than the products. Yeah, that's true. Because all we're doing with this energy is, we're going over the hump. So this is your activation energy supplied by the magnesium strip. So these, and since it's exothermic, then it is, reactants are thermodynamically more stable than the products. That's true. A is true. How about B? The reaction has a small equilibrium constant. We really can't tell that unless we do the calculations. Equilibrium constant, we should be able to do this calculation here and find out what the equilibrium constant is. Minus be positive. Well, let's just do it. 45.54 times 10 to the third joules. And that's equal to, I'm going to get rid of the negative sign because this is negative and this is negative. 8.3145 times temperature 298 and log K. So let's see, 45.54 exponent 3 divide by 8.3145 and divide by 298 yields 18.4 equals log K. So K equals e to that power. Yeah. 9.4 6 times 10 to the 7th. So that's true also. It looks like we're going to have to find which one is truer than the others. C says the ultraviolet light raises the temperature in the system. No, it doesn't. Didn't we say that it's well, the energy is not supplied by temperature. The energy is supplied by the energy of a photon. Right? So C is actually false. How about D? The negative value for delta S slows down the reaction. No. These are equilibrium expressions. Right? These are not kinetic expressions. Delta H, delta S, delta G, those are equilibrium. Right? They have nothing to do with kinetics. So D is also false. How about E? The reaction is spontaneous. Reaction is spontaneous, which is, yeah, delta G is negative. That's true. Spontaneous, but the reactions are kinetically stable. That's also true. They are kinetically stable because they require this activation energy, which is not supplied yet. Right? They'll just sit there and do nothing. Well, over the short term, they're relatively stable. So E is also true. Now, what we have to decide is which one is truer than the other. Well, I like E better than A or B. Thermodynamically more stable than the products. Well, that's true. That's a bad question. Right, because you got 3 possibilities. I should have substituted one in there more than one of the above. Then that would work. So if a question like that magically appears on a test, call me on it, okay? If I mark your answer wrong and you can give me that explanation, then you're guaranteed the points. Okay, 52. The equilibrium constant of a certain reaction was measured at various temperatures to give the plot below. Okay, so that's this equation right here is being plotted there. What is delta S for the reaction? Which part of that reaction has delta S in it? The intercept. The intercept log K equals 3.0. That's equal to delta S over R. Okay? So all we need is multiply this times R. Equals delta S. And that's about 25 in the neighborhood. Okay, so C is the best answer. Okay. I don't think I have another one for that one. So let's scroll to the next one. 56.
No, we already did 56.
All right.
We already did 56.
Oh, that's right. We skipped it from before. 57. That one valid? Okay. Y'all have to watch me. It's like getting ready to put me in a nursing home. For a certain process at 300 K, delta G is minus 12.2 and delta H is minus 7. If the process is carried out so that no useful work is performed, if no useful work is performed, it doesn't matter. Delta G is still what delta G is. Just because we don't get any work out of it doesn't change delta G at all. So delta G is minus 12.2 kilojoules. Man, that was a trick question. Now W would be 0. Okay. Oh, that's it.